Okay, so I think the audio level should be a little bit better now. I know a few people have mentioned that it's coming through not quite loudly enough, and my apologies. Unfortunately, because of the way YouTube works, I can't really. It's kind of difficult to go back and try and boost the volume. So let's appreciate the feedback. I'm going to try to improve things from here moving forward. I think it'll be easier if we need to bring the volume down in the future rather than having to try to bring it up. Um, so I've had some time here and there to try and work on some of the components, specifically continuing to work on the background compositor and how it works together with the RAM system that that I've been working on in the past. There was a lot of tweaking. I think maybe there's something to talk about another time. Some of the details of what I had to do. Um, Specifically, there are a few places where the NES kind of works in a very funky way, specifically with how it handles backgrounds. So here I can pull this up. So basically, right, any sprite or any background tile on the NES is 8 pixels by 8 pixels, which are very small. Um, and Basically, to make efficient use of memory and for programming purposes, on the NES, when you have backgrounds, instead of assigning a color palette to a single 8 pixel by 8 pixel tile, you assign a color palette to 2 by 2 tiles, so 16 pixels by 16 pixel part of the background gets assigned a single palette, and you have to do some really clever things to try and get the colors to look good. But basically, that's how the NES did it. And what I was finding was trying to write the code to follow that kind of logic. The way that the NES packs the bits into the structures for storing that palette information is just really annoying. And my goal is not to be a bit for bit replica of the NES, but to start and take inspiration from it. And one of the advantages we have is we do have a lot more memory than the NES did for video. A lot less than the SNES, but still a lot more than the NES. And so, the idea here is let's take advantage of the resources we have. And so instead of doing the system like on the NES, where it's defined for 16 pixel by 16 pixels and you get one color palette for that whole block, my system actually lets you assign a color for every tile individually, which is obviously more powerful. It can allow for more variations of the background colors for the background layer, and I think still gives us enough memory that we could probably have more than one background layer and try to bring in some fun SNES style things if we have the interest. But basically, other than it's mostly the same code. It's funny to look at it now because it's just so it's weird. It's just really, really really simplified. It takes forever for me to write this type of Verilog to really understand the problem that I need to solve. So you can see here, like I have a bunch of notes as I'm trying to figure out how to do the background tile attributes, is what they're called on the NES side. Um, and basically thinking about how we actually store the background tile data in memory. And then I also had to do some fiddling this way and that way to get the memory to work at all. Basically, our RAM, the timing of the RAM needed to work for the way that then the components that use the RAM, like our background compositor, depend on it. So basically, the idea is, on the negative edges of the clocks, the component can put in a request or read the data, and on the positive edges of the clock, our RAM component will actually then be going out and where is it? Our RAM. Here it is. So our RAM component actually gets the data ready on the positive edges of the clock. So the idea is negative edge, you can put in request. The next negative edge, you can read the data. And in the middle of those two negative clock edges, we have a positive edge where our RAM chip is actually going and retrieving the data for the address you requested. So it's a lot of just little dancing of thinking about how you do the timing for all these components on the negative edges, timing the number of cycles that it takes to prepare the data for the following tile. And we have plenty of clock cycles, so it's really not an issue. Our clock is derived from the pixel clock for the RGB signal that we're sending out and encoding over DVI to send to the TV. So we do have tons of clocks, right? Because this thing is running at, gosh, what's it running at? It's like 150 megahertz, I think. It's crazy overpowered. So plenty of time for us to go in and try and start to figure out basically for a certain X coordinate and Y coordinate, let's get the tile information, right? Then let's come in here, let's get the tile number. So the tile number then is going to tell us what the, where we have to go and get it from the pattern table. Then we get that tile information, which is 2 bytes. So we get the first set, the second byte. So, we have here the attribute tells us the colors. Over here, then these 2 bytes for the tiles tell us the actual pixel data that'll map to those colors. And we just set up some, some wires here with assignment so that it's always going to output red, green, and blue according to the appropriate color for that palette, and then the selected color, and then red, green, blue components. So yeah, so so that basically was how I ended up getting this to work. I think I did talk about getting the RAM to work in a basic way on the last recording that I did. But just as a reminder, what I've done is encoded a hex file for now as just an initial set of data. This is broken down and structured very similar to how the NES has structured its data for storage. I think I have that information over here. So these are the address ranges for the NES. I do need to update these to represent the actual layout that I'm using now for the video RAM data for the background layers. But basically, this is all copied from Super Mario Brothers byte for byte for now. So these are the pattern tables. These store background information, background tiles up here, and sprite tiles over here, or maybe the other way around, I think. Actually, these are the background tiles. Anyway, and then we have our name tables that then define, first we define attributes. Attributes define the colors. And, maybe later I'll show how this is laid out more clearly. But like I said, what we've done is set this up in a way that every tile, so every 8x8 tile can get assigned its own color. And that does give us a lot more flexibility with how we can do our coloring. It also does mean that there's more data, which may carry some challenges in the future. So if we have to, we may have to change it. I hope not, but it's possible. And yeah, so these are the tiles. Yeah, these are the tiles. Okay, so like 24 is a blank tile, just shows one of the background colors for the palette. And then over here are the attributes. So these just choose which palette to show for each of the tiles that are defined up here. And this is a lot of craziness basically while I was trying to figure out how to get this to work in a way similar to the NES, but in a way that works for our purposes. One of the many challenges we have is we have a widescreen display. It's high definition. How do we handle all this data? And I think, like I said, there will be more challenges that come. So right now, what I have is enough data defined for the entire screen. I think one of the things we'll have to do is figure out how to expand this to at least, allow us enough margin on the left, right, top, and bottom to be able to scroll smoothly up and down, that sort of thing. There's a ton to figure out there. But basically, this hex file for now compiles down and gets included with the bitstream, and it initializes the RAM that we have, our block RAM, to this data, which is cool. Because then our background compositor actually, as I showed over here, it actually pulls that data, every clock cycle, right? It does the right computations to figure out the data to show, and sets that up and gets the data ready. So, um, so here's what we have. So I'm super happy about this. We have gotten to the point where our background layers can be just as expressive, if not more expressive, than in the NES. Our colors, for example, are currently defined as 24-bit color. So you can have an incredible amount of variation, although today still one of these tiles can only be 4 colors, so it has still some limitations to be worked with. And we can still composite our sprite on top of our background layer, no problem. And yeah, so being able to define these tiles and get their metadata essentially correctly defining which color should be used for each of the tiles in here, right? So one thing always fun to point out is that these bushes are the same as the clouds. It's the same pixel data for the tile, and it's just a difference of the tile attributes that choose which palette to use over here and which palette to use up here. So lots of fun to be able to see things like this actually, in action and working. So there is a crazy huge number of things to do from here, which brings me to kind of what the next steps look like. So first of all, all of this stuff has been all of the code that's running on the system right now, everything is on GitHub. I did rename the project. It isn't HDMI output. That isn't really the point. It probably needs another rename at some point. I don't know. But Spartan Edge Accelerator graphical system, it's the best thing I could come up with quickly. It has all my sources in here. There's no documentation yet. That's definitely one of the things to be done. But there's a lot that still has to happen. So like I said, one thing is this background layer. I want to allow us the type of size for the background layer so that we can do things like smooth scrolling. Is one of the coolest things they had put in the NES at the time. It was very rare, and we want to be able to get that working in a system like this for sure. And that means that the background layer needs to have at least a certain amount of space on the left, right, top, and bottom. To be able to accommodate that. The other thing that's important is right now all of our background layer information is coming from the RAM, which is great, but our sprite isn't. Our sprite is still hard-coded. The location of our sprite, the graphics to use, the palette to use, the everything. So we'd want to take a look at how the NES or SNES handle their sprite information or character information, and adopt some of those systems and store that information in RAM so that it can be updated dynamically and the system can actually respond to those changes. The other thing that's going to be a lot of fun, and not quite sure how, but I think this might be the next thing I want to work on, is connecting our Xilinx FPGA to the ESP32 so that the ESP32 can actually write new data to our RAM, right? Because ultimately, if we want a program, I want the program to be able to run on the ESP32 that's on this board. And that means that it needs to be able to write data to the Xilinx FPGA's block RAM, and then all of our components, right, that do our backgrounds and sprites and things can just read from that RAM and display the correct image data. So I had started to look into this, and this is going to be something we'll follow up on. There are a number of connections that exist when you look at the schematic for this board that can theoretically or potentially allow us to load a lot of data. I mean, the QSPI is probably the most likely thing for us to use. As after the ESP32 has loaded data from the SD card and from the flash memory, the QSPI is available, and it hooks up to the ESP's QSPI connector, which is a pretty high bandwidth connection, and it hooks into the FPGA where we can write our own hardware to receive all the data as fast as possible. The thing that I'm stuck on a little bit, and I'll have to figure out, is what could we use to connect back? So loading data quickly from the ESP32, that looks like we have a path to success here probably. The part that I'm less sure of is we only want the ESP32 to load data into video RAM during a VBlank period, right? Basically, when the Xilinx FPGA isn't using the RAM to decide what to show on the screen, right? During a VBlank period, which is kind of up here in this virtual space above the image, is when we want the ESP32 to write data. So the ESP32 needs to be notified, probably via an interrupt, for when the Xilinx FPGA or when our graphics hardware has gone into VBlank. So then it knows, hey, this is my opportunity. I want to write as much data as I can into that VRAM before the graphics hardware starts to read from it again. So we'll see exactly how, I don't know, I think it's going to be quite an adventure to figure that part out. If this were a situation where we were spinning up our own board, it actually would be a lot easier because we can create whatever connections we want. And there are definitely other connections that I, don't need on this board that I could have taken advantage of to provide this sort of connection back from FPGA to microcontroller. So we'll have to see about that. So we got that. And we have documentation, we have improving our background layers, we have using the sprite, getting sprite data from RAM. I think after we do sprite data from RAM, that's when we'll look into supporting multiple sprites at the same time. We should be able to support at least the number that the NES supported, which is I think a total of 40 sprites and 10 per line, 10 being rendered per line. And we should be able to do more than that with the hardware that we have. We still have a lot of space on this FPGA, so we should be able to do a lot of fun stuff. So that's kind of the minimum things I'm already thinking about for next steps. One of the things I want to do is probably document each of those things here on the GitHub project as issues, so I can track them for my own sake. And look, if anybody else actually checks this project out, certainly feel free to start writing up other issues for improvements, helping out however you think you can. Yeah, it's really satisfying to be able to watch our little Mario bouncing around in his native habitat, natural environment. All right, I think that's about it for an update today. Really just wanted to show kind of how far we've come and then outline those next steps. So I'll include a link to this GitHub project in the description once I've finished streaming, and take care.